Conduction is how energy travels through a physical mass, and it does so using thermal motion. Thermal motion is disorganized random motion of constituent atoms in molecules with any body of matter. It also flows from higher energy to lower energy, from organized to disorganized, always down a thermodynamic gradient. You can see the ICATS 2006 evaporation condensation presentation to understand emissivity, which is a key component in understanding the thermal energy. It has to be emitted. It has to be transferred to the surface and then emitted as thermal energy or thermal radiation in order for us to see it. Well, that brings us to thermal energy, which is the kinetic energy of thermal motion, the translational, rotational, vibrational energy that's associated with a mass. With a thermal imaging device, we see that thermal energy as heat. Heat is the thermal energy transferred from a region of high temperature to a region of lower temperature. Mass stores thermal energy, or internal energy, and so heat equals the thermal energy in transit. Heat is easiest to detect using a thermal imaging device. Temperature is the measure of average value of the thermal energy of atoms and molecules, not the total amount of energy, thermal energy in a system. Look at the distribution curve below here. What most people don't realize is, let's say you have a glass of water that is 70 degrees Fahrenheit. Okay, what does that mean? That really means you're measuring the average of all the molecules that are in there and their motion, their ability to cause the thermometer, which is touching them, to vibrate in such a manner that the liquid inside of it, be it a metal liquid or other kind of liquid, that is mercury or other kind of liquid, expands, and then you can take a reading off of that. It's a measurement of that movement. The movement in those molecules is spread across a distribution curve. To the left on the curve that you're looking at the bottom here, that distribution curve says some of those molecules are probably near freezing, that is, near the point where they form ice. Okay, that's not absolute zero, that's not 0 Kelvin, but close to the temperature where they're moving ice. Now, some of that is also at the other extreme. It's got enough energy to become a gas, to leave the surface and to evaporate. If you don't believe that, put a glass of water on the table. In fact, put salt water on the table, so then you can see not only that it evaporates, but that somebody didn't pour it out while you weren't looking to get rid of the water. You'll find the salt left in there as evidence of the fact that that water evaporated. So some of that energy is at the high range, some is at the low range. Temperature is a measurement of the average value of the thermal energy of the atoms and molecules. Okay. It's a measure of the ability of randomly moving particles to impart that thermal energy to a thermometer, specifically to the fluid that's used in that thermometer to indicate the temperature. And the temperature in Celsius, that is the centigrade range, or in the Fahrenheit range. Kelvin, whichever you want to use. Well, which do you want to use? We will always use the Celsius or centigrade range. It's the international standard. We'll be working around the world. It's very helpful to know that you're communicating something meaningful to somebody else. But how did these ranges how are they developed? Well, the Fahrenheit scale, which we usually use in the United States, was Gabriel Daniel Fahrenheit. And he created a reproducible thermometer which used mercury, so it didn't wick up the sides of the glass, because it would normally wick and it's hard to read. Do I read this upper portion or the lower portion? Where do I take that measurement? Well, mercury doesn't do this, and so it gives you a good level to read. So he invented that in glass around 1750 AD. He set the 0 point at the lowest temperature of the winter of 1709. He is said to have used his wife's body, this is unknown if it's actually true or if it's an urban legend, but his wife's body heat to set the set the 100 degree point. But this resulted in a freezing and boiling point that were at partial degrees. So he stretched that range, and body heat became, so boiling became 212, so it was a full range, and her body heat suddenly dropped to 96.8 degrees. And then freezing was moved to 32 degrees. So both of them were whole degrees. So there's 180 degrees difference between freezing and boiling. So it's not a centigrade, that is, it's not a 100 gradient distance between the two, it's 180 degrees. That'll be important in a minute when we multiply one times the other by 1.8 in order to translate it from one to another. Okay. Celsius scale. Celsius was a Swedish astronomer, and he set 0 as the point where water froze, and he measured that many times to make sure that that was the right one. That was ice. Ice was formed in pure water at 1 atmosphere of pressure. So 100 became the boiling point of water. So that is a centigrade, right? It's 100 centa, 100 gradients between the freezing point or melting point and the boiling point of water. Boiling point is where, of course, it starts more energetically to go into a gas form or evaporate. Also, that's where it starts to condense more, and the colder it is, the more it will condense, of course. You lose the energy. Remember, this is vibrational energy. So as it vibrates, it gets farther apart. It goes from an ice where it's a solid, it translates to another form of matter that's a liquid, and then at some point it goes into a gas, and that's at 100 degrees. That happens more energetically. 100 degrees Celsius, 212 degrees Fahrenheit. Okay, so the relationship between Fahrenheit and Celsius in degrees can be expressed by these formula down here, the various formula. There's only one that you need of that, and I would encourage you to memorize, and that is the one in red, of course, that the temperature in Celsius is equal to 1.8 times the degrees in Fahrenheit minus 32 degrees. The reason I say that is there's only two here. They're expressed differently. Okay, the top and the bottom are just different, or rather the left and right in each top and bottom are only different expressions of the same one. And so if you memorize one, you can figure out the other one if you're in the field. So it's helpful to understand a little about the scales and why they were developed and how the gradation went, and why Celsius is called used to be called the centigrade scale. Take a little bit of a mental break here, because you don't really need to know Kelvin too much, but you do need to know what it is and what it means and how it became there. In thermodynamics proper, they will use the Kelvin scale. Lord Kelvin was one of the earliest scientists to consider the issues in thermodynamics, really one of about 6 to 8 men that really added huge amounts to the understanding of heat and how it was given. His actual name was William Thomson, without a P. He was a Scot living in Belfast, what we in America would call Scotch-Irish. They're actually Scots that were living in Belfast, moved there for political reasons by the king, and we're still having issues with that today. But he debated with Joule about the nature of thermal energy itself and the caloric theory, where heat was considered to be a type of invisible fluid called the caloric. We still have calories as a unit of heat, but the caloric theory itself was different from that. It's no longer believed by anyone. But he detailed, Lord Kelvin that is, detailed several theories of thermodynamics and was the first science to enter the House of Lords. Okay, this is where he derives his title, Lord Kelvin, from his schooling at Glasgow University, where the river Kelvin blends into the river Clyde. Well, he was given the title of the first Baron Kelvin. So that's why we name him Lord Kelvin. To the left here you can see some different temperatures in the Kelvin scale and kind of understand where he was headed and how it's used. Now, it is a centigrade scale. It is based on Celsius work, but it starts at absolute zero. So 0 Kelvin is no energy whatsoever. Nothing has ever been found to have 0 degrees Kelvin, and in my cosmology, if correct, that is the point at which a solid object would cease to exist in our physical form and turn into what is really just now being at least rediscovered. Used to be called ether, now it's called dark matter and dark energy. That's probably the point where those that translate one into the other. Now, keep that secret. No one knows it yet. It'll take them 30 or 40 years to figure that out. But to give you an idea, helium itself boils at 4 degrees Kelvin, or minus 269 degrees Celsius. It's really cold. We used to use a liquid nitrogen to cool off a dewar in the old and very large thermal imaging devices, and the liquid nitrogen boils at 77 degrees Kelvin. Very, very cold material. Glad we don't have to haul that around anymore. Another unit of energy is a joule. It is heat from energy. We can always use a joule to describe that energy as work. More common in thermodynamics is the calorie. Remember, not the caloric theory, but the measurement of a calorie. By definition, 1 calorie is the amount of heat required to change temperature of 1 gram of water by 1 degree Celsius. Now look on your screen, realize that a gram of water is about that which would fill that 0 degrees by the Celsius, that degree indicator. If you put it in there, it would just about fill that on a flat screen. It's a very small amount of water. So 1 gram is the weight at 1 atmosphere of 1 cubic millimeter of water. Now in food we use kilocalories, or a large C. So 1 food calorie, a calorie of food, is actually 1,000 calories, or a kilocalorie. Now Joule argued in 1845 that the mechanical power exerted to turn a magnetoelectric device is converted into the heat evolved by the passage of the currents of the induction through its coils, and on the other hand, that is the motive power of the electromagnetic machine is obtained at the expense of the heat due to the chemical reactions of the battery by which it is worked. In other words, he recognized the energy of the battery was being turned into work energy by the coils. Some of that was heat, some of that was work. So he is therefore credited with the first law of thermodynamics, discovering it and describing it. Okay, both the first and second law are found in his Christian defense of the Creator being the only being that could create or destroy energy. So his worldview of God, the God of the Bible being the Creator, caused him to look at the scientific evidence in a specific way. And when he was told that the energy from a fire is higher than there's more energy in the fire, it's more energetic than the water it heats, the claim was that that energy was being destroyed, and Joule stated it this way: there is an enormous loss of vis vita, or work energy, in the passage of the heat from the furnace to the boiler. Believing that the power to destroy belongs to the Creator alone, I affirm that any theory which carried out demands the annihilation of force is necessarily erroneous. In other words, they'd come to the wrong conclusion because only the Creator himself could create energy or destroy it. So that's the first law. Energy is not now being created or destroyed. That's also the second law. What happened to that energy? It's directly implied here. The energy was just lost, or entropy increased. So he restated the first law and directly implies the second law, claiming the energy had to have been lost to the system, or it's become less organized, or entropy increased. That's the second law. Right guy.